Math 1314, Section IC1, Spring 2022, Tyler Junior College, Section 5.3, Relations, Functions, and Function Notation, Video 1, Relations and Functions. We're about to open up something that is going to permeate the rest of the course, specifically functions. But before I say, here's what a function is, I need to lay a foundation so that we can develop and define clearly what a function is. In order to define a function, we have to define three terms first. The first of which is a relation. And in math, a relation is just a set of ordered pairs. You know, like the things that you put dots on a graph to represent. And there's a variety of ways to represent relations. So I just want to show you some examples. For example, we could open up a set by using some braces and then just start typing some ordered pairs. For example, I could type 1, 4. Now, there doesn't have to be a reason why the 4 is paired with the 1. But usually, not always though, usually when two objects are paired together in an ordered pair, there's some inherent reason why, but technically they could just be randomly paired together. For example, I could pair 2 with the number 5, and I could pair 3 with the number 6. And a lot of times, if there is some sort of pattern, you can probably pick up on it. For example, what do you think the next ordered pair would be? Now, you can look at it one of two ways, within each pair or moving from pair to pair. But what I'd really like you to ask yourself is, what is the relationship between this number and the number paired with it? In other words, what can I do to the 1 to get a 4 that would also turn a 2 into a 5, that would also turn a 3 into a 6? If you said add 3, then that's exactly what I was going for. Now, of course, the next one in this pair, if we just continue the pattern, would be 4, 7. But again, there doesn't have to be a rhyme or reason or even a pattern. I could throw in some other random number like 92 and ask you what's paired with it. And if you pick up on the pattern connecting the two numbers within a pair, that the second number is 3 more than the first number, then you could figure out that 92 would be paired with the 95. But again, the definition of relation does not require a reason for one number to be paired with another. There usually is a reason, but it doesn't have to be. Now, this is not the only way that you can represent a relation. Listing it as a set of ordered pairs is just literally what the definition is, but we could also have something like this. We could get this ready here. We could have a table, and we'll call the first column X and the second column Y. You're not surprised that I'm calling them X and Y, because when we put points on a coordinate plane, the first coordinate is usually the X coordinate, and the second one is the Y coordinate. Although honestly, those specific letters are somewhat arbitrary. We can use any two letters we want, but when we don't have a reason to use specific letters, we just generically say X and Y. For example, I could say X is my first name, Chris. And Y, well, we'll pair stuff up within a second. And let's put my brother's name, Jason. And my other brother's name, Scott. And we'll put my dad's name, Lee. And we'll put my mom's name, Paula. Now, if you're wondering, why did I write names instead of numbers? Well, look at the definition of relation. It's a set of ordered pairs. It doesn't say they have to be pairs of numbers. They can be pairs of anything. For these, I'm going to pair my name with the number 5, Jason's name with the number 5, Scott's name with the number 5, but my dad's name with the number 3, and my mom's name with the number 5. And I bet you can figure out the reason I paired these numbers with those names. It's because that's how many letters are in the names that I wrote. Now, granted, my first name is actually Christopher, so if I'd written Christopher, then I would have paired it with 11. But again, there doesn't have to be a reason why I paired my name with the number 5. Excuse me, that was supposed to be red. It can just be some random pairing. But in this case, I did have a particular reason. And these are considered ordered pairs, being that the order matters. My name, 5 is different than 5, my name. So another way to represent a relation is using a table. But there's even more ways to represent relations. For example, I could draw this picture. As soon as I get my formatting ready, I could draw this picture. Hold on. And I can mark up the x-axis and the y-axis. And then I could just put some arbitrary dots. Now I can actually use some shapes here. So I'm going to use a star. Let me see how big the star is. That's a little too big. Let me see what other shapes I have here. A heart, it's also kind of big. An X, that's kind of big. Let's go back to the stars. Those seem to work. All right, and I'm just going to put some stars on this coordinate plane. For example, I'm going to put one right there, and I'll put one right above it, right about there. And I'll put one right here, and I'll put one right there, and let's put one right there. And you might be thinking, that's not a relation. That's just a bunch of stars on a graph. Well, maybe I should just use dots like we normally would. I was just trying to use some of the features of the Zoom whiteboard here. So I'm going to replace each of these dots, each of these stars with an actual ordered pair, or a point on the graph, if you will. Give me 1 second. This is not drawing the way I want. There we go. And I'm not sure if these are going to land in the exact same places they were a moment ago, but it doesn't really matter because I'm just putting some at random. And I believe I had one way back here. Now, why is this considered a relation? Well, because each point on the coordinate plane has an ordered pair associated with it. I could actually type out what relation this is by simply giving each ordered pair, for example. And I'm going to label them A, B, C, D, and E, just so that you know which ones I'm doing, which order. We'll call this one A, this one B, this one C, this one D, and this one E. And so the ordered pairs, if I were to type them in the order in the order associated with their labels, A, B, C, D, and E, the first ordered pair would be 2, 0. The second ordered pair would be 2, 1. The third ordered pair would be 1, 3. The fourth ordered pair would be 0, 2. And the fifth ordered pair looks like is -3, -1. And I'm assuming that you're comfortable plotting points on a coordinate plane, since that was a skill talked about in a previous video. Why is this not red anymore? That should be red. There we go. All right, so a graph represents a relation, and it doesn't just have to be a bunch of blank points. It could also be a connected graph, which you could generate from an equation. So for example, if we had the following equation, and again, all of these are examples of relations. If you had the following equation, let's just say y equals x squared, and I'll type this square up there in just a second. I have to get the formatting ready. But if you had like y equals x squared, well, we haven't done a whole lot of graphing, but this is something that we could plausibly graph. And without going through all the details as to why the graph is what it is, in a second, I wanted to make that thinner, so let's get rid of that. Make the line width skinnier. Oops. Promise you I have a plan. But if we were to graph this by finding a bunch of dots and connecting them, we would get a shape like this. It's a parabola. Make that graph a little bit thicker. So it'd start kind of in quadrant 2 and hook down, touch the origin, and then arch back up, kind of like a horseshoe shape. But that is technically a relation because every point on the graph represents an ordered pair. Now, what ordered pair is that dot? I don't know. If the graph were drawn accurately and the X and Y axis were labeled, I could count it off. But I know it represents an ordered pair, and all that matters. In fact, there's an infinite number of ordered pairs on this graph, because technically speaking, a point on a graph takes up no width, and so I can fit infinitely many of them on there. So every point on the graph implies an ordered pair, and I want to write that because that's the reason this is considered a relation. Every point on the graph represents an ordered pair. So a graph is technically considered a relation, just like an equation is considered a relation. Because with the equation, we could determine whether or not an ordered pair satisfies the equation, and therefore whether or not the ordered pair belongs to the relation. So for example, Determine which ordered pairs belong to the relation x equals the absolute value of y plus 1. I know that's an equation, but again, an equation can be considered a relation because it defines a set of ordered pairs. In other words, the pairs of numbers that make this equation true. And we're going to test all 4 of these ordered pairs to see if they belong to the relation, and the answer will be yes or no by simply substituting the values into the equation and seeing if it makes the equation true. For the ordered pair 5, 4, the x is 5 and the y is 4. So if I put a 5 where the x is in the equation, question mark over the equal sign, and a 4 where the y is in the equation, I get 5 equals the absolute value of 4, followed by a plus 1. And again, this is asking the question, are these equal? It's not telling that they're equal, which is why there's the question mark over the equal sign. So we're going to bring down the equal sign and work both sides separately. The left side is just 5, so there's nothing to work there. But on the right side, we have the absolute value of 4, which is 4. Haven't done the plus 1 yet. And of course, 4 plus 1 is 5. Since 5 is equal to 5, the answer to the question is yes. This ordered pair belongs to the relation. And we could do the same thing for the rest of them. I invite you to pause the video and see if you can figure out which of the remaining ordered pairs do belong to the relation x equals the absolute value of y plus 1.